Welcome today. Today we shall be discussing a topic: work, energy, and power. When exactly do we say that work is done? When exactly do we say that work is done? When exactly? Work is said to be done whenever a force applied to an object causes the object to move through a distance in the direction of the applied force. Imagine if Dangote truck got damaged on the road, maybe the car developed fault and could not move again, and the truck is laden with maybe 600 bags of cement or so, and about 3 boys, they were all trying to push the truck off the road. You agree with me that they will not be able to push that truck laden with 600 bags of cement, but they have applied force on that truck. So at this instance, will you say that work has been done? The answer is no. The reason is because the force they applied on the truck could not cause the truck to move a distance. So if force is applied on a body and the body did not move, no work is done on the body. So we'll say that work is done on a body if the force applied causes the body to move a distance in the direction of the applied force. So that said, we can now define work done as the product of the force applied on a body and the distance or the distance moved in a given direction. You can also say that work done is defined as the product of the force and the perpendicular distance moved by the object. Of course, it must be in the direction of the applied force. Imagine if you are towing or if you are driving a toy car, that toy car will move in your direction of your force. I hope you get me. Yeah, so that is it. Work done. The unit of work done is joules. So we can say mathematically that work done is equal to force times distance. Please, I want you to understand that distance is denoted by the letter S. Work done, W, is equal to force times distance. This D is because you are just in junior secondary. But the real symbol for distance is S. Okay? Work is measured in joules. Okay, let's look at this. Let's look at this. Let's look at this. You can see from this case that a man is dragging a box. But you see, in this case, this force that is on the rope, otherwise we call tension, is not horizontal. It's not acting on the box horizontally. It's acting on that box at an angle. So if we make a dotted line at this point, so that we have a horizontal plane and an angle is formed here, we can have it that this force which is acting inclined in this direction will be equal to, that the work done now will be equal to the horizontal component of this force. What do I mean by horizontal component? That is the effective value of this force in the horizontal direction, because this force you see here can cause this block to move vertically upwards. It can also cause this block to move in the horizontal direction, which is what you are seeing here now. So Because this force is not acting linearly on this block, therefore the work done will be equal to the force cos, that is F cos theta, times the distance, which is d, moved by the object. Don't worry, when we progress, I'll use example to explain this further to you. We can also have other illustrations. See this bodybuilder, putting a lot of force to lift the dumbbell. Can you see that as he's putting a force, the dumbbell is moving a distance from here to here? So we can also say in this case that work is done on this dumbbell. Okay? So work can be done in a field. And the field we are talking about in this case is gravitational field. Now, if an object is moving up, I need you to take note of that the direction of gravity is in vertically downwards. Gravity acts vertically downwards. And that is why if a body is falling from a height, it does that, under the influence of gravity. So we'll say that object is falling freely. So we can have it that, but in the case an object is thrown vertically upwards, or a boy climbs a set of steps, maybe in his school, as he's going up a height, he is actually doing work, but the work he's doing is against gravity. So that is why when you are climbing a step like this, you notice some strain around your legs. You notice that, hey, your leg is spinning you as you are climbing up, because you are going against gravity. Okay, so when that happens, the work done will be equal to the force, which we will call the weight of the body, times the vertical height moved by that object or body, as the case may be. So if an object is going vertically upwards, the work done by that object is given by mgh. But remember I said if you are moving vertically upwards, you are going against gravity. But also, if a body is moving downwards, or a body is falling from a height, gravity is said to do work on the body. So the work done on the body by gravity is also given by mgh. So work done is equal to mgh, where m is the mass of the body and g is acceleration due to gravity, and h is the vertical height above the ground. Please take note of what I'm saying. That the m you see in this equation is the mass of the body and measured in kilogram, and g is acceleration due to gravity, and h is the vertical height above the ground. So in this case, we can calculate work done. Okay. Now, before you'll be able to do work, you must have the ability in you to do the work. So we want to talk about energy. What is energy? Energy is the ability or the capacity to do work. If you don't have the energy, you won't be able to do any work. So both energy and work done, they have the same unit as joules. Energy is measured in joules, and work done is measured in joules. For our scope, we're going to limit our scope to mechanical energy. So we have two types of mechanical energy. When we say mechanical energy, I believe you are not thinking of a mechanic. When we say mechanical energy, it just simply means a type of energy or a form of energy that's possessed by a body that is either in motion or a body that is at rest. Moving bodies possess mechanical energy. So whenever we are talking about mechanical energy, I need you to have that in your mind, and that's what we're talking about. So, but there are two types of mechanical energy. Number one is kinetic energy. Number two is potential energy. We're going to be looking at them briefly. What is kinetic energy? Kinetic energy is the energy possessed by a body by reason of its motion. You can also say that this is the energy possessed by a body by virtue of its motion, by reason of its motion. Anyone you can remember, they mean the same thing. Or you can say because of its motion, you know, they are the same thing. So, mathematically speaking, the formula for kinetic energy is given as kinetic energy is equal to half mv squared, where m represents the mass of the body and v represents the velocity of the body. So kinetic energy is equal to half mv squared. Okay, let's look at potential energy. Potential energy of a body is defined as the energy possessed by a body by reason of its position. So for gravitational potential energy, it is given as mgh. The formula for gravitational potential energy is mgh, where m is equal to the mass of the body and g is acceleration due to gravity, and h is equal to the height above the ground. So it's enough for me to tell you from here that kinetic energy of a body depends on the mass of the body and also on the velocity of the body. Also here, the potential energy of a body depends on the mass of the body, on acceleration due to gravity. This is gravitational potential energy we're talking about. And it also depends on the height of the object above the ground. So we've talked about energy, we've talked about work done. What then is power? If I give two people the same task with the same implements to perform a given task, you might discover, let's say I ask them to clear a little portion of the school field, give them the same cutlass that have the same advantage. You will discover that these two people may not finish at the same time. So if I ask you, you will easily tell me that, hey, that Mr. A is more powerful than Mr. B. So by definition, what is power? Power simply means the rate at which work is done. Power simply means the rate at which work is done. So if we put that in the form of equation, we can see that power is equal to work done over time. The unit of power is what? We have other measurements of power. We can also measure power in horsepower. Okay? Remember that 1 horsepower is equal to 746 watts, approximately 750 watts. The actual value of 1 horsepower is 746, approximately 750 watts. So we can say that 1 horsepower is equal to 750 watts. Let's have some examples that borders on work done. A man drags a box to a distance of 15 meters while applying a force of 320 newtons. Calculate the work done by the man. I told you that work done is force, the product of force and the perpendicular distance. Okay, so we have it here that the distance S is equal to 15 meters and force, capital letter or F, force F is equal to 320 newtons. So we are looking for the work done. In this case, work done we don't know, but we know that work done is equal to force times distance, S. So let us substitute. If we substitute the values, we will have that work done is equal to force is 320 and distance is 15. So what is the work done? 320 times 15 is equal to 4800. Is equal to 4800. What did I tell you is the unit of work done? It has the same unit as energy. So work done is equal to, the unit of work done is joules, denoted with capital letter J. What amount of work is done when a mass, okay, this one now is work done, okay, in a force field. In this case now we're considering work done in this force field. Okay, let's get to the question. What amount of work is done when a mass of 8 kilograms is raised through a vertical height of 2.5 meters? Take G to be equal to 10 meters per second square. Okay, so we bring out the parameters. So we have here that mass, parameters given, mass M of the object is equal to 8 kg. Height H equals 2.5 meters. Acceleration due to gravity G were given as 10 meters per second square. So we are required to calculate the work done, W. We don't know it, but we know that work done in lifting the body up, which is work done against gravity, is equal to mgh, where m is the mass of the body, g is acceleration due to gravity, and h here is height above the ground. So we have it that work done is equal to, the mass given is 8, g is 10, and h is 2.5. So we have that work done is equal to 80 times 2.5. It's about 200. That's about 200. Work done is equal to 200 joules. All right. I need you to test yourself on this. I need you to test yourself. and see how far you can go. A boy of mass 70 kilograms stands on a table of height 1.5 meters. Calculate his potential energy as he stands on the table. Take G to be equal to 10 meters per second square. I trust you will be able to answer it. Let me give you a hint or a tip. Don't forget that potential energy is equal to mgh. I trust you have the answer now. Okay, let's take more calculations on kinetic energy. Say a boy of mass 40 kilograms runs from his class to the toilet to urinate with a velocity of 4 meters per second. It took him just 10 seconds to do that. Maybe he was very much pressed. Calculate the boy's kinetic energy. Sometimes not all parameters are just needed to calculate whatever we're looking for. You know that 10 seconds there is just to give you an idea of the time that elapsed during the time the boy runs, but we don't need it for that calculation. So what we'll just need here is what we are going to work with. Okay, so that said, let's go straight to what we have. So the mass of the boy, mass M is equal to 40 kilograms, and the boy ran with a speed, okay, velocity V equals 4 meters per second. We are required to calculate the boy's kinetic energy. We don't really know it, but you know that we have 10 seconds there, but we don't have need for it. It's just an information, because kinetic energy is equal to kinetic energy, Ke, is equal to half mv square. Is equal to half mv square. So we have that Ke equals half times m here is 40 and v is 4. Not just 4. Look at the formula. Formula is saying v square. So we're going to square this. When we do that, we're having that Ke is equal to half times 40 times 4 square is 16. You know that these two here, 20. So kinetic energy is equal to 20 times 16. 16 times 2 is 32. So you already know what it is. 16 times 20 is 320. Ke is equal to 320 joules. Okay. Let's take more question on power. So see that power is the rate at which work is done. So in this case, we say the work done by a man is 200 joules. If the man spends 2 minutes to execute this job, calculate the power of the man. Now, let's go. Parameters. We have work done equals 200 joules. Now, time spent, time T, is 2 minutes. You know, the SI unit of time is seconds, not minutes, not hour. So we are going to convert that time to seconds. How do we convert from minute to seconds? How do we do the conversion? Like I said, you know that 60 seconds make 1 minute. So if 60 seconds is equal to 1 minute, 2 minutes is equal to 120 seconds. A simple calculation. So this time in seconds is equal to 120 seconds. But power is equal to work done all over time, the rate at which work is done. So we have here that power P is equal to W over T. So we have power equals 200 all over 120. So we have 0 taking care of 0. 2 can comfortably go here. 2 into 20 is 10, into 12 is 6. 2 can still go. We're having 5 and 3. So power is equal to 5 over 3. So this is the same thing as saying 1 whole number 2 all over 3. If you convert this to decimal, we have that power is equal to 1.67 watts. Thank you for your time. Let us practice some questions from our ExamGuide app. I told you ExamGuide app is an app for every mobile student. If you actually want to smash your WAEC, your junior WAEC examination, I recommend this app for you to use it regularly to practice. The more you practice, the more you perfect, the more you advance in your knowledge. All right, let's go straight to the app. When a moving vehicle is brought to a complete stop, the kinetic energy is, when a moving vehicle is brought to a stop completely, what happens to the body's kinetic energy? Option A is constant. Option B, increased by 4 folds. C, increased by 2 folds. D, reduced by half. E, reduced to 0. So which one is the answer? Please take note of this. Whenever a body is brought to rest, the final velocity of that object or body is 0. So if the velocity is 0, I told you that kinetic energy depends on mass and velocity. Therefore, the kinetic energy is also 0. So the right option here is option E, which is to say that the kinetic energy reduced also to 0. Which of the following does not have kinetic energy? Let's look at it. A block 4 meters above the ground does not, so take note of that. A car in motion, a falling stone, a released bullet from a gun, falling water. Which of these does not have kinetic energy? A block 4 meters above the ground. That is the right answer. Why? If you just place a block 4 meters above the ground, the block is not in motion. As long as it is not in motion at that spot, it only possesses kinetic energy. So option A is the right option for that answer. Okay, we'll stop here for now. Please continue to practice.